So, yesterday we started off with pardon. Yeah, we started off with a passive second order low pass filter, right. And how did we come up with this in the first place? Well, we said well, if we we started off with the first order low pass filter and then decided that this will only roll off at 20 dB per decade, because the current here is V at high frequency is Vi by R and the impedance is 1 over SC. So, we basically get only first order roll off. To improve the roll off, we wanted to make sure that this current also decreases with frequency, and that will only happen when you replace R with an impedance which is increasing with frequency, correct. By the same token, so we started from a first order what do you call filter and went to a second order one. I mean, is there any other first order filter that you know which will give you first order low pass? Pardon? L and R, very good. So, basically okay, how can you use an L and an R to get a low pass filter? L is connected in place of the resistor, very good. And this is Vi. So, at high frequency, what is this current? I mean, it is small, but only at infinite frequency it is 0. At high frequency, what is the current? Vi, I mean, what is the output voltage at high frequency? It is a low pass filter. So, what is the output at high frequency? Almost it is very small. So, what is the voltage drop across the inductor is pretty much Vi. So, what is the current flowing through the inductor? Vi over SL, and that flows through resistor. So, at high frequency, what is the output voltage? Vi by SL times R at high frequency. Right. So, this is also again a first order, it is rolling off at high frequencies as 1 over S, right. So, this is a first order low pass filter. Now, if you want it to roll off at what do you call at 40 dB per decade, what do you think we should do? Replace yesterday, what did we do? What did we do here? Did we replace R with a capacitor or with an inductor, or we added see at at DC the impedance must be the same. Do you understand? At DC the impedance here was R, here also the impedance has to be the same at DC, and so likewise here the impedance here is R. So, what should we do? Add a capacitor in parallel with. So, this is an inductor L, this is R, this is, and this is Vi, all right. And so now again we go with the same logic. So, this is I is nothing but I of S is nothing but, okay, now you are going to tell me how we will derive the schematic. So, I is nothing but Vi minus by SL, okay, and what is VO in terms of I? Yes, Yeah, what is R parallel with 1 by SC?
R by 1 plus SCR
Times?
Vs V naught by
In terms of I.
in
So, I times
R by 1 plus
R by 1 plus R by 1 plus SC. Okay. So, I will multiply this by R and this by R. Okay. So, this is telling you that if you call this Vx, Vx of S is nothing but Vi minus Vo times R upon SL. So, how is Vx related to Vi minus Vo? In English, what does it mean? Vx is nothing but the, what is R by SL? What kind of operation is it? Integration, right? So, Vx is nothing but the integral of Vi minus Vo, and Vo is nothing but, yeah, Vo is nothing but a, take Vx of S and low pass filter, correct. So, so now how do we generate, if assuming we have we have Vi and Vo, how will we generate uh, Vi minus Vo times R by SL?
inverting configuration.
Pardon?
Inverting amplifier.
What are we supposed to,
Integrate.
what are we supposed to do?
We have to generate Vx.
We have to generate Vx. Vx is nothing but, we are adding Vi
Minus V.
with minus Vo. This is Vi, this is minus Vo. We have to add them with equal weights. So, these two resistors must be the same and they go into a and C is nothing but, how can C be equal to L by R? That is not dimensionally consistent, no?
C equal to L by R.
So, 1 by RC must be equal to
R by L.
R by L. So, C must be equal to
L by R.
L by R square like before. Okay. So, this will give you Vi minus Vo by times R by SL, but with an inversion. So, to get it back to what we want, what should we do? So, this is R and this is R. Okay. So, this is Vx. What do we do now? How do we generate, once we have Vx, how do we generate Vo? Low pass filter. Do we know how to make a low pass filter? What is the DC gain of the low pass filter? 1. Okay. So, what should, if this is R, what should the other resistor be? R, and this is C, and this output voltage is minus VO. But luckily it is actually minus VO that we need. So, what do? You connect these two here. So, we move that resistor there from there. Yeah. So, the only difference is the position of this resistor. Okay. Earlier it was across the first integrator, now it is across the second integrator. So, this resistor is basically what is also called the damping resistor, because if that resistor becomes infinite, what comment can we make about Q? What is the value of that resistor? I guess we should call this C1 and then this is C2. I will call this C. C1 must be chosen to be L over R square. Now, what happens if that resistor becomes infinite? Okay, in the previous circuit, what happens if the resistor becomes infinite? What happens in this circuit? If Q becomes infinite, what happens? Q becomes infinite, what happens to the denominator polynomial? So, where are the poles then? If Q becomes 0 infinite, where are the poles of the denominator? It is at? Please solve it and tell me. So, the poles are at will be at plus minus j omega p, and is that stable or unstable? Yeah, it is pretty much unstable because you are on the boundary between the. So, by adding this resistor QR, so if Q tends to infinity, what happens to this resistor? It is like not having that resistor, correct? It is like an open circuit. So, the moment you put that QR, the poles go from being on the j omega axis to being well inside the left half plane, and thereby damping the impulse response, right. So, that QR, that resistor is called the damping resistor. Okay, now let me now derive another structure which is fairly commonly used on account of its or the lesser number of components, lesser number of op amps actually. Okay. So, if so if I look at remember the first time we had drawn the circuit, this was basically, we said that this was what is this? This was R okay, and what was this? This was C1 and this was C2, and what was C1? L by R square. Okay. Now, if I think of this as a box, right, with two inputs VO and VI and one output, namely let us call that Vx, correct. So, how is Vx related to VO and Vi? Please write down, work it out. Okay, hold on, let us write it down carefully. Vx equals Vi. Why minus V naught? Vi plus V naught upon the current that flows into that R parallel C1 combination is Vi plus V naught divided by R, that multiplied by minus R by 1 plus SCR multiplied by minus 1. So, that goes away, all right, and therefore, what we have and this R go away. So, what we have is Vi plus V naught divided by 1 plus SCR. Okay, so now if I replace this blue box by some other contraption which gives me Vi plus Vo by 1 plus SCR, then I can eliminate 2 op amps, correct. So, what do you think, is there something that we can think of which will take Vi plus V naught and generate Vi plus V naught by 1 plus SCR? Okay, let us say you did not have V naught, we just had Vi. Is there something that you can think of which will generate Vi by 1 plus SCR? Do you understand the question? I have a voltage Vi, I need to generate an output voltage which is Vo, Vx, which is Vi by 1 plus SCR. What is the simplest circuit you can think of that will do it? Okay, what is it? Okay, so basically this is R, this is C. Okay. Now I have two inputs Vi and Vo, and I need to add them, and then what do you call and I need to low pass filter their sum. So, what do you think we can do? Add another branch in parallel with R. Okay, so if we do this, what is the transfer function we get? Yes, please work it out. V Vi plus V naught by 2 times 1 by 1 plus SC times R by 2. Okay. So, is there something we can do to kind of what do you call get back this? I mean, clearly, if we choose, let us say, instead of making this R and this R, if I make this 2R and make this 2R, then what will happen? That becomes 1 by 1 plus SCR. Okay. So, now the only problem is I am getting V naught plus Vi by 2 instead of 1. So, basically this voltage is going to be, I mean, if we had op amps like in the blue box, we would be able to get V naught plus Vi by 1 plus plus Vi divided by 1 plus SCR. Now we are getting a smaller voltage. So, what should we do to make sure that the same current flows there? The current that flows there in that resistor is what? The voltage Vx divided by the resistance, but the voltage is smaller. So, what should you do to that resistance? you should reduce the resistance so that the current basically, okay, right. So the idea is, I mean, so that is the idea behind this structure, where all this these extra op amps and all these things are replaced by just simply, I will call this R2, this is C1, this is R1, this is R1. Okay, what are we doing here? VO and VI are being added, right, and low pass filtered, okay, and so the and they will be now and that voltage basically is evidently going to be smaller than what it was in the op amp case, right. So we adjust the value of R2 so that the overall transfer function remains the same. All right. So this is basically, this is a very useful circuit in when you are building filters on PCBs, where you know every extra op amp and every extra component costs space and money, right. This basically gives you a second order filter transfer function with only one op amp. What comment can you make about driving another stage? If we load up VO with a resistor, what happens? It does not change the transfer function. What comment can you make about stray capacitance? Look carefully.
It's even without the effect of stability.
Yeah, at across C1, if there is stray capacitance, basically you will find that it is it will change the transfer function, right. But otherwise at other two nodes, basically it is fine, and that is the price you pay for. I mean, you must understand that there is no free lunch, right. So if you get rid of so many components, I mean, you will have to pay in pay somewhere else, right. Okay, you understand. Okay, so you know that's so this is a famous structure. This is called the Rausch filter. What is the DC gain? -1. How did we get that? Yeah, capacitance is open. Yeah, so basically this voltage is 0. So what is this current? 0. So what is this voltage? 0. This current is 0 at DC. So this current is VI by R1, and this current is the same VI by R1. So this voltage is VI. So what is the output voltage? Minus VI at DC. So the DC gain is -1. Okay. So I will leave it as an exercise for you to find the Q in terms of these component values, but let us try and find the omega naught in terms of component values. So at high frequency, this H of S we want to realize a 1 over S square over omega p square plus S over omega p q p plus 1. At high frequency, how does h of s behave? Omega p square over s square, correct? And okay, so now let us stare at this picture and see at high frequency what happens. At high frequency, what comment can you make about this voltage? It is very small. So, what is this current? Vi over R1. Okay. Now, all that current, where will it flow? Through C1. So, what is the voltage at that node at high frequency? Vi by SC1 R1, correct? Okay, so what is VO at high frequency? Or if you simply, if you simply recognize this as being an integrator, the output is nothing but minus Vi over SC1 R1 S square C1 R1 C2 R2. So, now what is omega p square therefore? Yes, Praneeth. Okay, omega p square is basically 1 over R1 R2 C1 C2. All right. And here we have 1, 2, 3, 4, 5 components, correct, and 3 parameters to control, right, namely DC gain, omega p and QP. So, you can you will still be able to choose 2 other these things independently. Does that make sense? Okay. Now, what comment can we make about so the frequency response at this node is second order low pass. It is of this form. It is minus, in this particular example, it is minus 1 over S square by omega p square plus S over omega p QP plus 1. Now, what is the transfer function here? Yeah. So, basically this will give you so this will be SC2 R2 by S square over omega p square plus S over omega p QP plus 1. So, this is again a non-inverting band. Is that clear? Okay. So, yeah. So, this is this is a fairly popular variant of this, which is used when people are building second order low pass filter, especially on discrete with discrete components, simply because of the economy of components that are used. So, of course, there is nothing comes for free. So, one problem is that the component while the component count is smaller, it is indeed sensitive to stray capacitance. At any stray capacitance in parallel with C1 will cause a deviation in the transfer function, right. And further, you can see that the input resistance is not in the active RC, when we had 3 op amps, the input impedance presented to the source in this case was simply R, right. Here, unfortunately, this is the this node is not virtual ground, right. So, the input impedance is not really R1, it is something else, but that is the price you pay for reduced component.